Hi, I'm Fernando. I'm a professor at UFMG in Brazil. And today I will present to you AnghaBench. That's a work that I did in collaboration with several colleagues from the Federal University of Minas Gerais in Brazil, together with Anderson Faustino from the State University of Maringá. These two universities are from Brazil. The goal of this paper is to describe a benchmark suite. But what's unusual about this collection is its size. It contains today more than 1 million compilable functions. These programs are all written in C, and they have been mined from open source repositories. Notice that I'm giving particular attention to this word, compilable. The programs in our benchmark suite can be compiled by any major C compiler. That includes mainstream compilers like Clang, GCC, ICC from Intel, but also more research-oriented compilers like CompCert, for instance. However, these programs, they don't really run. Well, you could run them if you want, but they will most likely incur in some undefined behavior if you do it. But don't be disheartened. Having a huge number of compilable programs is good for many things, as you will soon see. Additionally, an important contribution of this work is the recipe to produce benchmarks automatically. This recipe includes the techniques necessary to gather the benchmarks from open source repositories and the techniques to reconstruct the programs so that they are guaranteed to compile. For this process of reconstruction, we use type inference, and that's pretty much the same style of type inference that's used in functional programming languages such as Haskell and SML. And in the end, all this process gives us AnghaBench, the largest collection of compilable C programs publicly available today. This collection is available at our website. In this website, you can download different ensembles of benchmarks, like programs with a single function or programs with multiple functions, large and small functions, and such and such. Some of the benchmarks have also been organized into a browsable database, where you can search programs by similarity using different distance metrics. And you can find several studies that we have carried out in this code base. That's one of the benefits of having so many compilable programs. But something that you might be wondering is why to build this collection? What is it good for to have so many compilable programs if they cannot run? In this paper, we show how to use this collection of benchmarks to train compilers for code size reduction. In other words, we'll be showing how to perform predictive compilation using AnghaBench. However, much more can be done with it. We can use the collection to test compilers, for instance. We can use AnghaBench to find sequences of compiler optimizations that might crash the compiler. We have already had this experience. And not on compilers, we can stress test tools that read programs in general. For instance, some friends from the Federal University of Viçosa, also here in Brazil, have been using AnghaBench to know how many programs would fit into particular types of FPGAs. And we can use the collection to know more about programs. By program understanding, I mean that we can infer more information about code that we find in the wild. For instance, out of a bit more than 1 million programs, we have found that 986,000 have chordal interference graphs. That means that the problem of assigning physical registers to variables can be solved optimally for those programs. That's 95% of the collection, and given the large number of programs sampled, it's safe to assume that this proportion is likely to characterize other C programs. But in this paper, we shall focus on code size reduction. I'll be explaining how we can use AnghaBench to train a predictive compiler that's good at compressing programs. But before we talk about that, I'd like to show you how we can reconstruct programs. Program reconstruction is the process of grabbing a program and ensuring that it compiles. So for instance, if we download the C file from a repository, it will not compile immediately. Compilation will fail because some type definitions are missing in the program, like the type yes_list. What's the definition of this type? Or function find, for instance, we needed signature, otherwise this program will not compile. To solve all these issues, we have used a type inference engine for C. This technique, type inference for C, has been described in previous work. These are the two key papers. The tool itself, which is called TypeC, is available online. You can input a program and then it will infer all the definitions necessary to ensure that the program compiles. For our example, it would infer, for instance, that uint 8 is an integer, and would infer that yes_list is a structure type with at least one field. In this case, this field must be a pointer to integer, and would infer the missing declaration of find. So, to produce a benchmark, first we download C files from publicly available repositories in space we chose to crawl on GitHub. For each file, we can either infer types for it entirely, and in this case the entire file will become a compilable benchmark, or we can partition this file into individual functions. In this case, each function will become a single compilable C file. Now I will talk about one of the core applications of our benchmark suite. That's predictive compilation for code size reduction. I will start explaining what's predictive compilation. In a way, we could define it as the custom treatment of programs. Basically, a compiler has many optimizations and analysis that it could apply on a program. For instance, if we want to know how many optimizations and passes LLVM applies on a program at the -OS level, we could use the command in the figure. In this case, we are running the -OS level of optimizations, which is a sequence of optimizations to reduce code size. And that's what we get. Quite a lot of analysis and optimizations, as you can see. Some optimizations are applied multiple times. For instance, simplify CFG, an optimization that removes useless jumps, among other things, appears 7 times in this sequence. Something that's important to realize is that opt-OS is not the best code size reduction sequence for any program. opt-OS is a good guess of a sequence of optimizations that's likely to reduce code without impacting execution time too much, but it's just a kind of educated guess. For instance, let's consider this program. What it does, it's not really important to this presentation. Just consider that we have here a compilable C program. If we give this program to opt-OS, then it produces an LLVM intermediate representation with 74 instructions. But let's use instead a different sequence of optimizations. We shall use these 9 optimizations here. In this case, we obtain an intermediate representation with only 22 instructions. In other words, this customized sequence of optimization is able to produce an intermediate file that is 3.3 times shorter. But how can we find the sequence or similar sequences? Or in other words, how, given the program, could we determine a sequence of optimizations that is likely to reduce its target effectively? In fact, there are many ways. I will show in this presentation one technique. This technique consists into organizing programs into space. This space is given by a matrix that we extract from the program. For instance, let's consider a 3-dimensional space formed by the number of instructions in a program, the number of stores, and the number of nested loops that code contains. These are countable features that are unique per program. In other words, there exists a function that maps programs to these 3 features. And given some programs in this known universe, we can find good optimization sequences for them. How we find them is not very important. There are techniques for that. For instance, there are examples of genetic algorithms that have been adapted to find good optimization sequences for programs. They keep trying different sequences and evolving them until finding something that can be considered good enough. And notice that different programs don't have to be mapped to the same optimization sequence. In other words, we can use this exhaustive approach to find sequences that are good for programs in the known space, but they are not the same for each program is treated in its own way. So given that we have a map of a set of known programs to good optimization sequences, what do we do when we need to compile a known program? Basically, we find the programs in the known universe that are the closest to the unknown program. And given the parameters that make up our universe, this notion of distance is well defined. We can use, for instance, the Euclidean distance to measure the distance between two programs. Given that we know the good sequences for the known programs, we can use them to compute a candidate good sequence for the unknown program. There are many ways to do it. We could sample the most common optimizations, or simply take the sequence from the closest program, or try interpolation, name it. But the key idea is to use information about the known programs to predict the good optimizations for the unknown program. One problem with this methodology to build predictive compilers is that it requires a sample of known programs that cover the metric universe well. And it's relatively easy to leave huge portions of this universe uncovered. By uncovered, I mean that there is no program, the set of known programs in these regions. And what happens if we need to optimize an unknown program that falls exactly into the uncovered region? We will have to approximate its behavior with known programs that are too distant, or in other words, with programs that are too different to provide effective hints of what would be good optimization sequences in this case. And the results are bad predictions. We end up with wild guesses of what would be good optimizations for the unknown program. Wong and Aboyle subsum well the problem in the recent survey about machine learning compiler design. The most immediate problem continues to be gathering enough sufficient high-quality training data. Although there are numerous benchmark sites publicly available, the number of programs available is relatively sparse compared to the number that typical compiler will encounter in its lifetime. To demonstrate that AnghaBench is effective as a training set to predictive compilation, we have used it to train YACOS. YACOS is a framework for predictive compilation built on top of the LLVM compiler. You can know more about it in the paper that describes it, which came out last year. It has several different extractors that convert a program to a vector of program features. Some of these feature vectors come from dynamic program characteristics, like program counters, for instance. Other feature spaces are static. And in this paper, we have to use the static collection of features. That's a must. For our benchmarks, they don't really run. We took these features from a paper by Namulero et al. These features include static program characteristics like number of loops, number of instructions, number of arithmetic instructions, number of branches, and things like that. In total, that gives us a space of 46 dimensions to explore. Each program is a point in this space, and we can use Euclidean distance to find programs that are close. So given that we have this space, we need to associate points with it, which represent programs with sequence of optimizations. These are the known programs that we shall use to carry out predictive compilation. We take them from Angha. In this case, we chose the 10,000 largest programs from the Angha collection. So, given a program from this training set, we try 100 optimization sequences on it, each one with 60 optimizations. And then we collect results. Results are the code size of the target program. And in the end, we will have a map of 10,000 entries. Each entry is a program, and it's mapped to a list of 100 optimization sequences. These sequences are sorted out by the effect that they can obtain on target programs. We call this map an optimization cache. So, given an unknown program P, we find in the optimization cache the program P' that's the closest to P, using Euclidean distance on the numeral feature vectors. And then we choose among the sequence of P' the one that we shall use to compile P. That can be just one sequence, like the one that's the best for P. Let's call this strategy J1. Or we can choose the 10 best for P. Let's call this strategy J10. In this case, we apply them all on P. That will give us 10 binary files and we keep the smallest. Or we can choose, among all those sequences that improved over a baseline, say, OPT minus OC. I mean, those that, when applied onto P prime, yield code that's shorter than OPT minus OC applied onto P prime. That's called approach, the elite strategy. Anyways, there are several ways to choose the sequences from P prime that we shall apply on P. We have used the optimization cache to train echoes. Let me show you some results. The goal of this experiment will be to reduce the code size of the executable programs that LLVM generates. As benchmarks, we use the LLVM test suite, which contains 275 programs plus 13 programs taken from spec CPU Cint. We got programs from CPU 2006 actually. We will compare our benchmarks with other synthetic benchmarks. We shall see what happens when we vary the benchmarks in the training set. So we shall use CSmith and LTR Gen to generate training sets. These tools are program generators. They have been published in previous papers, and you can take a look into those papers if you want later on. We shall use each program generator to produce 10,000 programs. We will take the 10,000 largest programs from AnghaBench. For fairness, we will use each generator to produce a set the same size as Angha and then collect the 10,000 largest programs. So without much ado, let's take a look into the results that we obtain after training echoes with the different training sets. Each training set with 10,000 programs again. This table shows percentage of code reduction compared to Clang minus OC. So every cell is a percentage. And we show the worst case reduction, which we call minimum, also the average reduction, the median, and the best result, which is the maximum percentage of a reduction. For each training set, we will present results for the different ways to choose the candidate sequences in the optimization cache. If you don't remember anymore, J1 picks one sequence, J10 picks the 10 best sequences, the elite pick up the sequences that improve on the baseline. When we look into our worst result, we see that our predictive compiler has increased the size of many programs, sometimes by a large factor. The other training set had this bad result too, in the worst case. But on the average, we're doing pretty well. The results are positive for most of the training sets. And same for medians. And when we look at our best results, we can observe some very nice reductions. But the best way to use the predictive compilers is with baseline, meaning that we can try a prediction plus that baseline and then pick up predictions only if they surpass the baseline. We can still use the same metrics as before, except that now it makes sense to count the number of programs in which we do better. Notice that now we no longer have negative results. We are only picking results in which we did better than the baseline. And from the initial collection of 288 programs, we usually could outperform the baseline in most of them. And results are pretty good for other metrics too. For instance, on average, using the elite strategy, we produce code that's 11% shorter than Clang minus OC when compiling 280 programs. And if you consider all the 288 programs, including negative results, our average is still positive. And typically better than the other approach, by the way. Anyways, you can find more about these results in the paper. Let me conclude the presentation. This paper has thus presented AnghaBench, a collection of compilable C programs, which is publicly available, and you can browse the programs right now if you want. For brevity, in this presentation, we talked only about a handful of results. However, many more are available in the paper or in the companion technical report. And if you are interested in the work, please get in touch. So I think that's it. Thank you.